My name is Anna Steffi, and I am part of Group 19. This is recitation 5.
I'm Zach Barnett, and I'm also part of Group 19.
I'm Alana Jabalis.
I'm Zhongling Jia in Group 19.
All right, and so for problem 1, it was a little different because the force was being applied to the top box. Do you want me to go through my approach first, or did someone else want to explain their answer first?
Personally, I like your answer. I will say that.
Gia, did you have an answer that you wanted to talk about, or did your answer look like mine?
My answer is kind of different, but I think I'm wrong about it. But I do want to ask, like, why we could use the F equals m, like the mass times acceleration, because I think the acceleration is 0, and I just don't get the idea.
Oh, why do you think the acceleration is 0?
Yeah.
Well, I said, oh, go on.
Yeah, I'm thinking like it's moving in a constant speed, but I'm not sure like how to do it another way.
I didn't really get the sense that it was necessarily a constant speed. Just kind of, it was talking about almost starting off, because they're talking about like the boxes will move together across the ice without slipping. And that, when that comes to my mind, that means they're not already moving.
Okay.
Like,
Yeah.
So it's not constant speed. Okay. Yeah, I get the idea now.
Yeah, so I just, I couldn't get through this unless I drew these diagrams. This is the tiny box and that's the big box. Yeah, I knew what I needed for my friction. So to get the friction of force exerted on the top box by the bottom box, I still like look back at this. Here's my pen. Yeah, I think that's what I did. I think I knew that the friction, they had to be like equal, like the friction exerted on the top box by the bottom box was going to be like yeah, they have to, it's like the same force. And I know that treating it as a system, the bottom box will move with the top box when you put that force on it that we're talking about. And that's really the only force that we're considering right now, considering that it's on an ice rink. And so that's what I was looking for here. And I just did not specify that in my notation, that like these, like I could have put like Fs equals negative, like Fs1 or something like that. But yeah, and then that's mass times acceleration, and the mass is of the system with my 2 boxes. Then I solve for acceleration, and then I can just put it back into basically another Fs. And then this is also the 2 masses that kind of looks like, I think it's like EU or something, a friction constant, but it's not. So for part two, did you want to explain your answer?
Yeah, it's pretty straightforward. So for the maximum amount of force that you can apply and the boxes won't slip on each other, I think that's basically saying, you know, that the force applied and the friction force are going to be equal to each other. So not one outweighs the other. So they're exactly equal, nothing slips basically. So, and I said specifically the mass of the top box, I believe would be the factor in that. So the force applied would equal the static friction times mass and gravity, which is the natural force.
Mhm.
Wait, so are you just saying that as long as like the force of friction is greater than, would F net be just the force applied?
I think F net would take into account everything that's going on, not necessarily just the force applied.
Yeah, so then would the force of friction have to be greater than F net or just like the force applied?
Well, I think the force of friction would have to be greater than or equal to the force applied
Oh,
for
okay.
it to not slip.
Yeah, that's the equation for the force, for the friction constant. And we're looking for the magnitude of force exerting on the top box, which is not the magnitude of the frictional constant, but yet another magnitude of force that we are exerting on something.
Yeah, you're right. I think my logic, again, maybe wrong.
No,
My logic was
like,
that it would be the same in this situation.
Mm,
Because I think that for the maximum amount of force you could apply, it would be the same as the friction force going against it.
Mm,
interesting.
That's this entire execution. It's interesting.
yeah.
Mhm.
Yeah, and if you have concerns about it, I'm down to talk about it because like I said, I'm not 100% confident, but this is what I thought.
Well, what I did is I took that and I said that equal to my force, but instead of putting force, I put mass times acceleration.
Mhm.
And then I isolated acceleration. And then I put it basically back in the equation. Yeah, that's all I did. So yeah, I put that to it's equal to the same force. So my answer is like a lot longer because I wish I could write it down, but it's like very long.
Can you like take a picture and like upload it or something, or?
I'm gonna write it down, but I don't know why I did this though, now that I'm coming back to this. Yeah. It's a static constant, that's the normal force, if it would write the normal force. And this is static constant times the mass times the gravity. And I agree with him in what it says up here. And I do this times mass times gravity, big M Oh, that's where it's different. The largest. This is different. Because this is so I set the force here. I think they have different weights. And why do I think that matters? Does that make like any sense? Because again,
Yeah, I mean, are you talking we use different masses? Is that what you're saying?
US equals anything times 2. And so, let's put M. And then that is just comes in there. So my answer. Little M plus big M over big M.
I guess I think the main or one of the main differences in my logic is I didn't take into account the bottom block. I'm not sure if I think the weight of the bottom block really matters too much.
Yeah, me neither.
Yeah, I think all that matters is if the top block moves on it or not. Because it's a frictionless surface on the bottom anyways, so.
Okay, you guys can go on talking about the other ones. I'm thinking about my answer.
Okay. And for part 3, I think possibly more work could be done. I'm not sure. But you know, testing what the acceleration of the box is if you're pushing the top box with a force magnitude large enough so the box is slipped. So I said in that situation, if the box is slipped, bottom, we know the bottom block is not going to move at all, so the duration is going to be 0 because no force is being applied to it. And then that means that all the force that is being applied is going to the top block. So we know that the force that is being applied divided by the mass of that top block is equal to the top block's acceleration. And that was my overall answer for that.
Alana or Gia, do you have anything to say about that?
Oh.
I don't really know. I'm like trying to process it. Is when you wrote F, is that just force applied?
Yeah, I was not very good about labeling these things. That's my fault. But yeah, that's the force applied.
Would you have to, I didn't really think this through yet. Would you have to like subtract the frictional force at all? Or no? Like I have no idea. I'm not like trying to make you doubt yourself, but
I don't know, because this is a situation where it overcomes friction.
oh, okay.
So I'm not sure if you'd have to really take into account.
But I think there still is friction, right? It's just not
No,
enough.
I see what you mean. Yeah.
Yeah.
I would just, sorry, you can
Okay.
go first. Oh, I was just trying to think like, so there's no, we are assuming that there's no fictionalized, or is that,
Say it one more time.
oh, are we assuming that there's no fictionalized?
That's, yeah, that's what I'm assuming. I'm assuming that's why they labeled it and
Okay,
gave us the question they did.
okay. I need to like do it over again. I count that as,
Gotcha.
yeah.
Yeah, I'm really not sure if we would have to take into account the friction force. Thing.
Cause, oh, wait.
Because I mean, you're right. I mean, like if I'm envisioning like pushing a really heavy object, I can get it to move, but it doesn't mean like it's on ice. It's not like it's moving as easy as it would be on ice. It still takes a lot of effort to move that same object, if that makes sense. So maybe you do have to take it into account.
It's just if you're finding only the acceleration of the top, would you use like F net? I don't know if that made sense. Or would you only use like the force onto the top box?
My thinking was that you would only use the force onto the top block. The force that's being applied to the top block would be the only thing causing it to move.
Okay.
Now, if there's friction, I'm not sure.
All right, I'm back.
Okay.
Um,
Do you have any thoughts on what we were talking about?
no, I didn't take care of something. Um,
For part 3, is the F putting for the top block, the F net like contains the force being applied and the friction force, or it's not? It's just the pushing force.
I think F net would include both of those forces.
Yeah. And are we using F net in this equation in the document?
That I do not know.
Um,
A what? Sorry, I'm just looking at the thing. I'm trying to read it out.
And the thing is, if we do have to take friction into account, then it makes me think the bottom block would also move.
If what?
Because we're talking about for part 3, if it's just the force applied, or if we have to take into account friction still, and subtract by that.
Oh,
Yeah. I have force is mass times acceleration plus the friction, so it's force minus the kinetic friction constant is mass times acceleration. And then, yeah, I isolate my acceleration and then,
Yeah, I think that would be
Yeah.
right for part 3.
Force friction. Okay. So the bottom block then.
yeah, I guess the bottom block would move because if it's moving without it slipping, then it would probably still move too, even when it does slip. But I don't know how you would rate that. Or is it not moving? Oh yeah, is the bottom block moving?
The thing is, if we have to take into account friction for the top block, I feel like I have to say that the bottom block is moving then.
Oh, because the friction is, wait,
Well, no. Okay. Because if I think about it, like the bottom block is on the frictional surface. If I start pushing the top block and then the bottom block moves, the top block is no longer slipping. If both are moving, the top block cannot be slipping because both are going to be moving at the same speed. So it can't be moving.
well, hold on. I think I don't know if this makes sense, but since like the force of friction is moving in the negative x direction, there. Oh wait, but does that have any effect on the block below it?
okay,
Like, could that be pushing the block slightly backwards? Or not pushing it backwards, but like making it decelerate slightly?
I think if we're taking into account the friction, you could think about it as the top block pulling along the bottom block, or the bottom block pulling along the top block. I don't think anything's being pushed back.
Oh, okay.
I don't know.
Yeah, I think it would still like move forward, but there is like that force of friction going in the opposite direction, but it's probably like too small. I don't know.
Yeah, the thing is, I mean, if we're thinking about it, like the whole system is on a frictionless
Oh.
surface. If there's any amount of friction between those two blocks, the whole system's going to move. And if the whole system's going to move, I think it's going to move at a constant speed.
have to draw out this freaking diagram again. So insert on it. It's in relation to that other block. And this bigger block. Capital N. Mhm. Um, I can use like different notation this time. So this is going to be so nice. Okay, and so net this stuff, and well, that doesn't really matter. So we're looking at both accelerations. So if we want to find the acceleration for the top block, this is going to be the net force is mass times acceleration, right? So we have two acting forces here. So this isn't hard at all. I don't know why I'm looking at this. So it's just this times this because they're opposite, right? That's mass times acceleration. Cute. So now we're going to solve for this acceleration. Okay. Equals 10. Everyone in agreement. Cute. And so the issue is that Fk, we all know, is just this friction constant, and that's normal force. But we know that normal force is tiny mass, because again, this is in relation to the top box, which is that thing, which is the negatives, or the combination of all these forces. That's what that is. And so the acceleration of box A is this. And that was really discoverable by just drawing that little diagram. And for the bottom one, I would assume, because it's just the acceleration of M is just the like force onto M2. It only has one type of force, and it is that friction. So we can do a lot better, and to shorthand it, it would be really similar. It would just be that frictional force, mg, and then the reason why that's down there, this is big M, is because I got here by forces mass times acceleration. And so this is for block 1, that's block 2. This is small block. This is big block. Yeah.
Yeah, this is straightforward.
That's what I wrote out.
I agree. Like, it's
Okay. And briefly explain how the rate of change of momentum of the two system boxes. Oh, by the way, I think this is garbage up here. I don't know what I was thinking. This won't erase for me. Down here. Explain briefly how the rate of change of the momentum of the two block system is related to the force you exert on the top box in each of the 3 cases above.
Well, I think I wrote this kind of based off assumptions in part 3, so I think some adjustments definitely be made to this.
I would just say that they're equal to each other in every case. Because isn't like, I have in my notes. Oh, we haven't even gotten to that part yet. Oops. Over dt. And like we're only applying a force.
I mean, yeah, I guess so.
Same mass of the two blocks will be traveling faster and faster. Threshold with the force over construction. Top mass much faster at the same amount. Okay. Let's go through this one real quick. This picture will display, I guess we don't need it for recitation because you can see it on the actual document. I think on Google, I mean, not on Google, on Zoom, it's acting up. But it asks a small block of mass M is attached to a spring of stiffness Ks and related length L. The other end of the spring is attached to a fixed point on a low friction table. The block slides on the table in a circular path, and radius of R is larger than L. How long does it take for the block to go around once? And this is something I took from my notes. And the only force acting on the block that we care about is the spring Fs, and we know that Fs is this, which I have, this should be together, hopefully. Yeah, and I have that like, it's just the difference. And I just put them together, therefore these are equal to each other. And I'm going to solve for V because that's what we're looking for. No, we're looking for time, but I know that time is distance over that. And we want T. So this is going to be that, it's just to solve for, and then we put it in there, in that equation. And I remember this also from like the A to B, like the homework questions. It's just 2 pi times the radius. So that would be the distance. And it was like 1/4 2 pi times like 50. That's what we did in the homework to find like equations just like this. So that's why I put that there.
Yeah, I agree with this. This makes a lot of sense.
Okay. This is fine with me. This is fine. We're gonna have to stop the recording real quick.